Hello, testing. Is this on? All right, let's get started. Welcome to Data 8 Lecture 9. Today we're going to be talking about histograms. Some announcements. So just a reminder that homework 3 was released yesterday and is due on Friday. Project 1 is going to get released tomorrow, and it is a partner project. So you should find a partner within your lab because we'll have some sections of lab time dedicated for you and your partner to work on the project together. Okay, so try to find a partner within your lab, and you two will work on project 1 together. There will be some deadlines for that I'll point out when we announce it. I would like to also point your attention to the resources page on our Data 8 website. Whoa, fix yourself. Okay, so if you go to Data 8 Summer 17 and go to the top nav bar, you can't see it now, but in the links here, there's a resources page. I just want to make you aware that this page exists and it has some helpful information. So here is some stuff when we start talking about exams. If you scroll down, we're going to start linking to solutions to the homework and labs here. So do keep an eye out for those. In addition to that, we've compiled a list of additional questions for our data sets here. So these are completely optional. Basically, if you would like to get more practice and want to do your own independent data analysis, these questions we think will provide a good starting point for you. So for example, if I scroll down here, let's say I was really interested in the census data. I can click there and jump to it. It gives me a line of code I can run to read in the table, and then a question. This only has one question, but for example, I'm asking here, has the female to male ratio changed over time? Yesterday, we only looked at the ratio in 1 year, 2015. You can also ask the question, has it changed over time? Okay, so some interesting questions here that may provide a starting point for your own independent data analysis, especially if you're like more practice with Python or if you're interested in a particular data set. Okay, so that's the resources page, and that's all I got for announcements. Any questions? Cool. So let me recap really quickly what we did yesterday on bar charts. Okay, so we started off by talking about types of data. We noted that in this class we work with, roughly speaking, 2 types of data. Okay, we work with numerical data, where every value is a number and from a numerical scale. Because they're numbers, they can be ordered, and the order is meaningful. The differences between the values are also meaningful because it's numerical. On the other hand, we have categorical data, where instead of having values from a fixed scale, they come from a fixed inventory, a set of values. Those values may or may not have an ordering. And typically, when we compare values, we're just asking whether you're in a category or not in a category. We also noted yesterday that just because values are numbers, it doesn't necessarily mean that our data is numerical. Okay, so our example from yesterday was the example from the census data. In the sex column of the census data, we had 0, 1, and 2. However, those values are not numerical data because it doesn't really make sense to compare like 0 to 1 and 1 to 2 as numbers. Instead, they represent categories. So in that case, we're working with categorical data, not numerical data, even though the values in our column were numbers. Okay. Lastly, we talked about bar charts. Bar charts allow us to compare quantity across different categories. We looked at examples yesterday of smartphone owners who use their phone for the following. So we had different categories of uses, and the lengths of each bar was a proportion of people that used the smartphone for that particular thing. We also looked at yesterday the gross ticket sales for individual movies. So we can use a bar chart to compare the gross ticket sales for Star Wars, compare it to Avatar, use a bar chart to quickly compare different amounts that way. Okay, so to briefly recap what we did, I have here the top movies table from yesterday. And if you recall, I made a bar chart yesterday that looked like this. Okay, so I took the top 10 movies. These are a list of the top grossing movies. And I took the top 10 movies, range 10. Okay, so top 10 movies. And to do a bar chart, I can just do bar H, and I pass in the categories and then the column that I want to say how long each bar is. So I'm going to take column 0, the title, and column 2, the gross amount. Make a bar chart out of that, and bam, there we go. Okay, so any questions about that? Cool. So now that that's fresh in your mind, please discuss with your partner how you would create a bar chart that looks like this. Okay? So right here, I have the top 10 highest grossing movies, like I had earlier. But instead of putting the amount each movie made, I have here the age of the movie. Okay? So how long ago each movie was released. If you'll recall from the table does contain the titles of the movies. And for each movie, it contains a column containing the year the movie was released, but not how long ago the movie was released. Please talk with your partner about how you would create a bar chart that looks like this.
Minus whatever year it was released. You can just do like 2017 minus table.com of year release. And that'll be an operation done on every item.
All right. Any ideas? Yes, name?
I'm Andy.
Andy.
You could do the current year. You could do a new comment the current year minus the year it was released.
Yeah, so Andy says, I can make a new column in my table that is the current year, so 2017, minus the age column from the previous table. So you're saying, take this year column and do 2017 minus this. That gives me the age. And then you're saying I can do a bar chart after that. Great. So let's do that. So right here, I want to take my top table, add a column age, and I'll do what Andy says, 2017 minus top.column age. Okay, so what I'm saying here is take my column age and subtract each number from 2017. Let's see what I get. And it's an error. The column age is not in the table. Sorry, year. OK, so what do I have? I have now the column containing the age of each movie from 2017, so this year. And now all I have to do is save that in a variable. I don't have to save it in a variable, but in this case, it makes my life a little bit easier. I'll take the top 10, range 10, and I want to do a bar chart with the title and the age. All right, so there we go. We created the table successfully. Cool. So now I can go. So now if you remember from yesterday, I also used the group method to compute a distribution. Okay. So yesterday we were wondering how often, like what were the most prolific studios in this table? So which studios released the most successful movies? So what I can do there is I can take my top table, I can group by the studio. The way group works, if you'll recall, is that it goes through my studio column and counts up how many times each studio appears. Okay, so when I do that, I have every studio, one row for every studio in my previous table. And for every studio, I counted up how many times it appears. Okay, so I have here Disney appeared 29 times, Fox appeared 26 times. And yesterday, we did a bar chart of that. Okay, so I take my studios and plot a chart with the count. And there you go. And now I see that Disney made a lot of movies, Paramount did, Paramount/DreamWorks did. So there's kind of some funky thing going on here with studios like merging and becoming like one big studio. Python is not super smart about like distinguishing between Paramount and Paramount/DreamWorks. It just says if you're spelled the same way, I'll put you into one bar. Okay, so do know, for example, here Warner Brothers and Warner Bros. New Line, there's some interesting stuff going on there. Be careful with your data, but this kind of roughly contains the information we're looking for. Okay, so we have here a distribution of the studios. How many times each studio appeared in my original table, because I had the studio and how many times it appeared. Okay, so I did a distribution of the studios. I can also look at a distribution of the ages. Okay, so I have here my age table. Sorry, my aged table. Right here, I have a bunch of ages. I can find out how many times different ages appear. Why would I want to know that? Well, maybe it's the case that younger movies had more gross box office sales than older movies. Okay, so maybe they made more money than older movies. We would expect that to be the case, right? Because we know that inflation, this number here is not adjusted for inflation. But let's see if that really is the case. So let's take my age table, aged, and let's group by the age. I now have a table containing the age of each movie and how many movies were that age. So for example, there were 6 movies that were released in 2015, so 2 years ago. On the other hand, there were only 3 movies that were released 9 years ago. All right, I can take a bar chart of that. So let me bar chart the age with the count like we did earlier. And now I get this long guy. Okay, so this is a really long bar chart. And what I have here are the ages. And I have here on the x-axis how many times each age appeared. So I see, OK, there's a bunch of 2s, an 8, a 13, a 15. And it's really long. Okay, so it's not entirely clear to me. So I did compute a distribution of the ages. But from this visualization, it's pretty hard to tell. It's pretty hard to tell like what exactly is going on, what trends are there. And that's because this visualization answers a different question than the one that I was thinking in my head. Okay, so this visualization here lets me answer what kind of question? It lets me answer the question, were there more 5-year-old movies than 4-year-old movies? Or were there more 8-year-old movies and 9-year-old movies? But that's not really the question that I'm interested in. What I'm interested in is, overall, like, were there more younger movies in this table than older movies, right? And so this visualization is not that great at answering that question. How might we resolve this issue? I'm so glad you asked, because that's the next topic we're going into today. OK, so to briefly recap, now we're talking about distributions. Okay, so how many times different items appear in my table? The distribution is the frequency of different values, as we've seen before, and we can use the group method to compute distributions. So it'll go through a column, count up how many times each value appears, and then make a new table out of that. Okay, so we use bar charts to show the distribution of categorical variables, right? So when we're working with the studios, it makes a lot of sense to use a bar chart there, because we can see each studio, how many times it appeared. So we can use bar charts to say, for example, proportion of US residents that are male or female, because male and female is a categorical variable. And as before, we use it to kind of say how many times each studio appeared. Okay, so now let's talk about binning. Okay, so it looks like bar charts are not exactly the thing to do when we have numerical data, right? So just imagine if I had older movies in my table, that bar chart would have extended really, really far down, right? So if I had movies from like the past 200 years, now my table is like, off my screen. Okay, so when we're working with numerical data, we like to use this thing called binning. Our problem with our visualization before was that it compared individual years. We're not super interested in individual years. We're instead interested in kind of like, are younger movies more common than older movies, right? We're interested in overall trends. So we can use binning to kind of lump the numbers together and see what the overall trend is. Okay, so when we bin numerical values, all we really do is instead of counting each value separately, we just say, OK, this value falls within this range, this value falls within another range, and we call those ranges bins. Okay? The way we define bins is that we say, OK, this bin goes from 10 to 20. And typically, the range for a bin is inclusive on the left side. So if I have these numbers and I have these bins, let's take 188. 188 will fall into this bin. 170 will go into this bin. So here's a 185, 190 bin. So again, this notation here, the bracket on the left side means inclusive, 185. But 190 will go into the next bin over here, because it's exclusive on the right side. Okay, so 170 would go here, etc. Place all the numbers into the bins. And now I have binned my counts. Okay. So you can kind of see how binning kind of solves our problem earlier, where we don't want to compare individual years. Now we can compare bins instead of individual numbers and get a better sense of the overall trend of our data. All right? Any questions about that? Yeah, Kevin?
Do bins have to be evenly spaced or can it be unevenly spaced?
So Kevin asked, do bins have to be evenly spaced or can they be unevenly spaced? Great question. Typically, it depends on the data. Usually we'll do evenly spaced bins at first, but sometimes there are cases where uneven bins are result in a more, let's say, accurate histogram or distribution. Okay? And we'll see examples of that today. So if we take these bins and use them as and make a quote-unquote bar chart out of these instead of using the individual accounts, we get what's called a histogram. It displays a distribution of numerical values. Okay? So basically the same as a bar chart, but instead of using the individual numbers as categories, we bin them together and then take a bar chart, draw bars for each of the bins. All right? So let's do that. Scroll past all of that. You know what? I'm just going to get rid of that. It's too long. Okay? So I'm going to take my age table. Group by age. So now I have the ages. These are individual ages, so let's try to bin them together. To bin things together, all I have to do is call .bin. Okay, so if I call .bin on age, what you see here is a table containing a bin column and the age count column. The way this table works is that this here is the left bound of each bin. So this bin goes from 2 to 11.4, and there are 41 movies that fall within that bin. Here I have 11.4 to 20.8, and there were 40 movies that fall within that bin, etc. Okay? Now, there's one row omitted here. Let's take a look at that last row. You can see that this last row contains the 96, and there's 0 things that fall into that bin. That's because when we're defining a bin, we need both lower and upper bounds. So right here, this is saying this bin goes from 86.6 to 96. Only one item fell into there. If we didn't have this row here, we wouldn't know where this bin ended. Okay, so we need that row. Now, you might be asking, why is there like strange 11.4, 20.8 when there are no such values in my original table? That's because what bin does by default is it takes my original data and just says, OK, I'm going to divide it into 10 equal sections. So it takes my lowest age, my highest age, does like a division, creates 10 bins, and just throws stuff into those 10 bins. Okay, so typically we'll want to define our own bins. And the way to do that is to just specify an additional bins argument. Okay, so bins equals, and I can make an array of, let's say I want to bin 0, 20, 40, 60 by 20s. I can do 0, 20, 40, 60, 80, 100. And if I do that, now I have a little bit more reasonable looking bins. And I can see here the distribution of ages within those bins. Yeah, Kevin?
So is that 100 at the end? Is the last item of the chart supposed to be the upper bound of the 80 to 100 bin, or is it 100 and above?
Right, so Kevin's asking, is this 100 here representing the bin 80 to 100, or does it mean 100 and above? The first thing you said there was correct. So this bin, this 100 here, is saying the bin goes from 80 to 100. Comes afterward, or so this is not 100 and above, this is just 80 to 100. Okay, cool. Any questions about that? Yeah.
Well, if that's the case, how do you explain for 0 that there are 75 counts? Isn't it true that 100 is the age 100 and above, 80 is 80 to 100, 60 is 60 to 80, and so on?
Sorry, could you repeat your question?
I was just curious about the way you phrased that. You said the 100 bin was 80 to 100. Isn't the 100 bin 100 and up?
Isn't the 100 bin 100 and up? Well, I'm just saying in this specific example, the 100 kind of represents the end of the 80 to 100 bin. I actually think you're correct in that if I remove the 100 and just do 60 to 80, well, actually, it looks like here it's still 0. So when we're doing bins, this is actually just the upper bound. There actually are movies that go above, but we don't count them. Because when we're talking about bins and we specify exactly the bins that we want, basically we don't we want to just know the upper bound. We don't want to do 100 and above. It's not that useful for doing a histogram. So we're going to be using this in the context of histograms. And when you're drawing a histogram, it doesn't really help you to draw like a bin 100 and above, because you're just going to draw like one flat line going on into infinity. So typically, you specify some endpoint there. Good question, though. OK. So as a reminder, so as a shortcut, instead of using make array, you can just use a list instead. So I can do that. This also works. This does the same thing. And if you're extra special, you'll remember that np.arange will do the same thing as I want here. So I can do 0 to 101 increments of 20. I do want to put 101 here because it won't go. If I put 100, it'll stop at 80. Okay? So if I do that, I get the same thing. Okay? So a bunch of different ways to get the same thing. And now to make a histogram. To make a histogram, I can just do h.hist. If I do that, then I get a histogram. Okay, so I get the ages here, the bins here, and the counts of each bin plotted on this chart here. So again, these bins, if you notice and look at these bins kind of like don't align exactly with the grid lines on this chart here. And that's because, again, when you don't specify bins, Python will just say, OK, I'm just going to create some bins for you. And those bins are not necessarily like perfectly aligned on each line here. If you want to align them yourself, again, you can just specify the bins. So I can just take my bins here, do that, and there you go. Okay, so I'm looking at a histogram here. I have the bins 0 through 20, 20 to 40, 40 to 60. And I'm plotted for each bin how high it is depending on how many things fall inside. Okay, so what do I notice about this? I do notice that there are more younger movies than there are older movies. Okay, so I can get that information by using a histogram, by looking at the distribution of ages in my table. Cool. So now you might be looking at this histogram and you're wondering, why is there like this weird percent per unit thing, and why are these numbers like so strange, and they don't seem to correspond to the actual numbers in my original table? I'm going to go into that later. But if you do want to make it use a count instead of this weird percent per unit thing, you can pass normed equals false. I'm going to explain this in just a sec. But if I pass normed equals false, it does the counts instead of like this percent per unit thing. Okay, so right here I have about 75 movies fall into like the 0 through 20 bin, about 60 movies fall into 20 to 40. That should be familiar, hopefully, to you guys after we looked at bar charts. OK, any questions about that? OK, so let's take a look. Now it's time for, oh, hello, smiley face. Let's take attendance. So I don't know why I did that, because I'm going to click here. And I'm going to open up the form. And go for it. OK, give you guys a minute to do that. All right, let's keep going. So why did histogram use that weird percent per unit thing before? Okay, so by default, histograms use this idea called a density scale. Okay, and what that means is, by default, when you call .hist, what we're trying to ensure is that the area of the chart, so the area of each bar added together, sums up to 100%. Okay, so what that means is on the horizontal axis, we have, for example, the age. On the vertical axis, we have this unit called percent per year. And the reason we do that is because when the horizontal axis is year and the vertical axis is percent per year, when we compute the area of that bar, we do percent per year times year, which the units cancel that, and we get just percent. So we get like this bar has 20% of my overall population, my overall like table distribution. And then my next bar contains like 15%, and then 10%, and then 5%. So all the percents need to sum to 100%. Okay, so the area of the bar is a percentage of the entire thing. Now, why might that be useful? Why don't I just stick to my normal counts? Well, so Kevin mentioned very conveniently that we can use different sized bins for my data. Okay, so let's suppose that I take my age, and let's say that I want finer bins. So instead of counting up by 20, I count up by 5. Okay, so I do that. And now we see here histogram, and we have, instead of bins by 20, we have bins by 5. So we see more detail in my histogram here. Okay. Now, in particular with this histogram, it looks to me like it goes up and then goes down slowly. And it looks like down here, there's kind of like, it goes up here and then down, and then down, and then up, and then down, right? And that level of detail here maybe is a little bit too much for me. Maybe I want to say, OK, I just want to show the overall trend of it going up here. But over here, I don't really care about this detail. I want to smooth it out by combining bins into a bigger bin. Okay, so the way to do that is just to specify different bins. So I can take that, and instead of doing 1 to 100, that'd be 5, what I can do here is make a list. So here we go, 0, 5, 10, 15. I have an easier way, np.arange, 0 to 101 by 5, and then just copy that. I have a bunch of bins. This does the same thing. Okay, and let's say I want to smooth out that bin right here. So I want to say, OK, instead of doing 5s here, I just want to do one bin from 80 to 100. I can just do that, 80 to 100. There we go. Okay. Let's say I want to do 60 to 80. So let's keep going. 60 to 80. Take away the bins in the middle here. Let's make that look a little nicer. 60 to 80. And then let's do that. OK. So I have 60 to 80. And OK, so I had this kind of big looking thing. Let's say I do 45 to 60. Okay, so 40 to 60. 40 to 60, delete those bins. And we get this really big bar over here. What happened here? Talk with your neighbor about why those bars look so much bigger than they did before. I see maybe like 10 people talking. Introduce yourself to your neighbor. Talk about why this is happening. Why is this bar so big? Why can't I use counts? Okay, so discuss why. Why is it so big?
I guess there are like not many players that are 2.6 years of age. But it's just less detail. We're not counting by 5, we're counting by like 20 here.
OK, so any opinions? Why did I lose my shape of my distribution, right? So before, my distribution looked like something kind of nice. So I had np.arange, 0 to 101 by 5s. Before, my distribution looked like this. So it goes up and then down. Now it looks like my distribution goes up and then down and then really high up and then down. Why does that happen? I'm going to wait 10 seconds. Yes, in the back.
Sean, and it's because it's taking all of them from 40 to 60 and adding them. And this is exactly what
Yeah, so Sean says, so you're saying that this is actually correct. This is a correct behavior. Is that what you're saying? Like, we're actually saying, OK, we are taking this bin from 40 to 60, and there actually are like 42 movies that fall into the bin 40 to 60. That's why this bar is so tall. Any other opinions? OK, so Sean is correct. So this is actually correct. So right here, there actually are, if I scroll back up, or if I just use aged.bin, and I've been on age, take my bins here. So if I actually were to count up the number of movies that fall into my bin, you'll see that from 40 to 60, there are actually 44 movies that fall into the bin. That makes sense, right? Because as I increase the size of my bin, more and more movies will fall into that bin. However, this has a downside that when I take a histogram and use the counts, my bars will just get taller and taller the bigger I make my bins. Okay? So that's obviously not exactly what I want, because this is pretty misleading, right? It looks to me visually when I look at this that there's a lot of movies that are between 40 to 60 years of age, and not as many movies that are 0 to 20 years of age. And that's not correct based on what we've looked at here. It's misleading. And the reason why it's misleading is that because it violates the area principle. So if you remember from yesterday's lecture, at the very beginning I had an example with like the cars and like the cars getting bigger. Okay, so right here what's happening is this bar is getting too big. And in fact, if I were to take even more bins out, so the more bins I take out, the worse this histogram looks, until finally I just get one massive bar here, right? And it looks like all the movies fall here and none of the movies fall here. Okay, so it just gets worse and worse the bigger I make my bins. That's why we use the density scale. Okay, so the density scale it says instead of making the bars as high as the number of movies, the actual like straight up number, what it says is let's make it as high. Let's make sure each bar area corresponds to the actual proportion, the percentage of movies that fall within that bin. Okay, so if I were to take that and remove this evil norm equals false argument, now we see something that looks more reasonable, right? It looks like this still contains, okay, so this bin is still like pretty big, but I still have the original shape of my distribution. It's not misleading to me in like this big of a sense, okay? Okay, so the way this works, the way that we actually find the heights of these bars is, let's do that, how to calculate height. Okay, so we know that we can't use a count. We can't use a straight up number of movies that fall into the bin to find the height. We need something a little bit more sophisticated. And to do that thing, the one thing that we need to remember is that the area of the bin, the area of that bar, needs to correspond to the proportion of movies that fall within that bar. So if I have one bar here with 30% of the movies and one bar here with like the other 70%, I need to make sure the area of those bars are 30% and 70%. I'm not using the counts. I'm using kind of like the area distributed over how long that bar is. Okay, so to calculate my height, let's suppose that my 20 to 40 bin contains 59 out of my 200 movies. Okay, so that corresponds to 29.5% of what my 100% of movies. So I want my width times my height to equal to 29.5%. Okay, my width in this case is 20 years. Okay, and that means that my height needs to be 29.5% divided by 20 years to get me about 1.475% per year. So again, my width is already 20. My area needs to be something else. My area needs to be 29.5. So that means my height has to be 1.475% per year. So that's where these strange looking units come from. This percent per unit thing that you see when you use hist normally comes out because we're using the density scale by default when we're drawing histograms. Okay, so to find the height of this bar, we take the percent divided by the width of the bar. Cool. And how do we, so if we can't use the count to interpret the height, so if we're not counting the actual number of movies, how do we interpret this strange looking 1.475% per year? Well, one interpretation is that the height measures the density in that bar. Okay, so what we're saying here is that this bar contains 20 years. Every time I step forward by 1 year, I get like 1.475% of my total movies. I step forward another year, I get another 1.475%. So on average, in that bin of 20 years, I have 1.475% for every year. Okay, so it measures the density. So again, to show you the formula, we use percent in bin divided by the width of the bin. And the height measures the percent of the data in the bin relative to the amount of space in the bin. Okay, so that strange looking expression there really just means if I have like 30 movies in my bin, and I stretch out my bin really far, like let's say I make my bin twice as long, right? If I have 30 movies before, and I make my bin twice as long, now my bin would be half as tall, right? And that's the behavior that we want, because if we keep the bin size, if we keep the height of the bar the same, so let's say I had 30 movies here, and I make my bin twice as long, and I still keep it at the same height, 30 movies per bin, now my bar looks like it has twice the area. Okay, so that's where the misleading area thing comes out of. It's because when we adjust the width of our bin, the heights don't adjust to maintain the same amount of proportion, the same area. Okay, so the height here is representative of the density within the bin. So what we're saying here is that if my bin is really small and I have a lot of movies in there, it'll be really tall, because every time I step forward 1 year, I'll get a lot more proportion of movies, so lots of movies. If my bin is really long, my bin you can think of it as being less dense. So the less movies fall into there per year. So if I step forward 1 year, I get on average less movies than before. Okay, so my height kind of measures my density, my percent per unit. Any questions about that? Okay. So I have one more slide here where the area in the bin is, as before, if we just work backwards from before, the percent in my bin is just the height times the width, because my area represents a percent. So if I want to answer the question, how many individuals fall within my bin, like say 20 to 40, I want to find the area and then look at how many total movies there were. So if this bin contains 20% of all my movies, and I had 100 movies total, then this bin contains 20 movies. Okay? So I can still get back my original count, but I can also answer the question, how crowded is my bin? I use the height to look at how crowded is my bin. My height measures the density within that bin. Okay? So to kind of look at my examples here, okay, so let's take a look at this example. Right here, this is saying, okay, my bin from 40 to 100, if I look at the bins, my bin from 40 to 100 contains 65 of my movies. Okay? So my width of the bin is 60. So first, this bin contains 65 of my movies. I had 200 movies total. That means that this bar, this bin right here, contains about 32%. 32% of all my movies. Okay, so the area of this bar here needs to be about 32%. The width of my bar is 60, right? Because it goes from 40 to 100. The width of my bar is 60. The area of my bar needs to be 30-some%. So if I just work out the math, width times height, I see that the height of my bar needs to be about 0.5. Okay, so 0.5. So there's an example for you guys to think about. When HIST draws my histogram, it does that same calculation for every single bin that I have here. So all of these are percent per units. Because I'm using the density scale, I can still retain the shape of my histogram even if I change the size of my bins. Okay? Any questions about that? It's a little odd that there are no questions. So how about this? Let's look at my bins. Find out estimate with your partner what the height of my bar here should be if, instead of using 0 and 5 and 10 as my bins, if I just had one bin containing all the movies between 0 and 10 years of age. Okay, so find out what the height of that bin should be with your partner. Go.
For the heights. I know it's relatively in space there are.
All right, so to do that, what we want to do is find out how many movies there are total in my bin 0 to 10. And that means that we have 33 movies in my bin 0 through 10, which corresponds to, because we have 200 movies total, that corresponds to about 16% of my original area. 16% of my original area divided by the width of my bin, 0 through 10, which is 10, comes out to about 1.6% per unit. I can actually just take a look at this. So remove my 5 bin there, and we can see that right here we get about 1.6, 1.7, close enough, close enough. Okay, so that's how you calculate the height of a bin in this density scale. Okay, so to briefly recap, first of all, is anyone still taking attendance? Very good, closing that. Okay. So to briefly recap, we first talked about bar charts yesterday. In a bar chart, we have one categorical axis. So typically when we draw a horizontal bar chart, we get the categories on the y-axis, and one numerical axis. Since we're drawing categorical data, the bars, it doesn't really matter how far apart they are as long as they're equally spaced apart and the width of the bars are the same. When we're using a bar chart to draw a distribution, we make the lengths of the bars or the heights of the bars proportional to the percent of things that fall within that category. Histograms, on the other hand, are used for numerical data. Okay? So when we draw a histogram, because the horizontal axis is numerical, so there's no gap between 10 to 20 and 20 to 30 and 30 to 40. Because it's numerical, we draw without any spaces in between each bar. The height measures the density instead of the count or the proportion. The area is what measures the proportion. The area is what measures how many things fall into that bar. Okay? Cool. So now I'm going to show you little nice things about histograms. We can use, let's say we want to compare two different distributions. So I'm going to take this table. This table contains some data that the scientist named Galton collected a long time ago. Now, Galton was kind of a weird guy. We'll learn about him in the future. But just know that in this particular table, what he did was he looked at the heights of people and compared them to the heights of their mother and their father. Okay? So it looks like this guy right here was 73.2 inches. And his father was 78.5 inches tall. Mother was 67 inches tall. Okay? Now we can draw a histogram of the distribution of the heights of the suns. So if I take the heights dot hist sun, I get back this thing, which looks like most people were about 70 to 72 inches tall, right? And I can also take a histogram, heights dot hist, of the fathers. So father. I can see here that most of the fathers were between, let's say, 67.5 to 70 inches tall. So it looks like the fathers were a little bit shorter than their sons. However, it's a little bit hard to compare these histograms because I have to scroll back and forth, up and down, and because I have to worry about my axes not lining up, right? So this 62.5 here is not perfectly aligned up with this one right here. 70 is not lined up with 70, so comparing these two like this is kind of hard. So a neat little thing you can do is if you pass in multiple arguments into hist, it will overlay a histogram for each one of the columns you pass in. And so very snazzy. We have here a distribution of the sons in yellow and a distribution of the fathers in blue. And now we can compare them more easily. We see here that the sons on average were a little bit taller than their fathers. Okay. Why not go all the way? So I can take both sons, fathers, and their mothers and compare all of them. So the coloring gets kind of strange, but you just need to look at this legend here. So the blue is the sons, yellow is the fathers. Yellow is the fathers, and the dark blue are the mothers. Okay. So we can see here that the sons are on average taller than both their moms and their dads. Okay. Any questions about that? Yeah. Can I change the color? Sean asked, can I change the color? Let's see. So I look at heights.hist. perhaps there's an option here that lets me change the color. Okay, so I use heights.hist question mark, look at my documentation here. Perhaps there is, although it looks like based on what's here, it's not easy. So it's not particularly easy to do that, unfortunately. Good question. All right, so let's take a look. Another thing that I can do with hist, conveniently enough, is I can change the units. So like if I do hist and use unit equals, so if I take that and say my units are inches, then it'll label the x-axis with inch. Just a convenient thing to do. Okay. And if I want to change, so let's say I want to specify my bin. So let's make this more complicated. So I want to make my histogram like ready for publication. So I want to draw that, specify my bins, np.a range. Let's say 55 to 80, increments of 1. And my unit is inches. So now I have bins that I specified myself that are aligned with the axes lines here, the grid lines. I can still see the shape of my distribution. I have this thing down here. And if I want to change the x-axis label, I can do plt.xlabel. And I can say what my label of my axis is here, so inches, like that. And now I have height inches on the bottom, and I have percent per inch on the y-axis. All right, so this is looking pretty nice. Now again, this is not letting me directly compare each son to his father, right? I'm comparing here the overall distributions of sons, mothers, and fathers, okay? So I'm saying from this visualization, I can answer the question, on average, were sons taller than their fathers? On average, were sons taller than their mothers? Okay? I can't do a comparison between sons and fathers directly. I can't compare individual sons to their fathers. But I can compare the overall shape of distribution, which is pretty handy. If I did want to compare individual sons to their fathers, remember from a couple days ago, we talked about scatter plots. We want to use a scatter plot for that. So heights.scatter, son with their father. And now I get this thing right here, which shows me every son, the son's height on the x-axis and his father's height on the y-axis. Now I can do a direct comparison and see, OK, it looks like when fathers are tall, their sons are also tall. Okay. So that's the kind of thing I can answer with a scatter plot. This right here is what I can answer with a histogram, overlaying histograms. Cool. A neat little shortcut that you can use when working with histograms like this, when you want to overlay them, is to know that if I want, so by default, .hist will do a histogram for every column in my table. That's the default behavior, which means that I don't need to actually specify any of these guys. I can just take them all out and do bins. And what that would do is it would say, OK, my original table had sons, fathers, and mothers. If you don't give me any arguments, if you don't say exactly which columns you want to draw, I'll draw all of them. So I'll draw that. And now I have the same thing, but with less typing. However, you do have to be careful, because if I did have something that I couldn't put into a histogram there, and trying to do .hist without specifying the columns, it would give me some type of strange error. So do be aware of that. But neat little shortcut if you want to save some typing. Cool. I can also overlay scatter plots. So if I do height.scatter, the way overlaying scatter plots work is that I specify what I want on the x-axis as the first argument. And what this method will do is it will look at my heights table and say, OK, sons goes on the x-axis. All my other columns go on the y-axis. Okay, so father, I draw in one color. Mother, I draw in another color. If I had something else like uncle, I would draw an uncle in another color. So if I do that, I get back the son, fathers, and mothers, each with their own color. And now I can see them all together in one scatter plot. What kinds of questions would the scatter plot answer? I'll leave that as an exercise for you. I'll see you tomorrow. Hey. How's it going?
Kevin.
Kevin?
Yeah,
Nice to meet you. Sam?
So I was sick this past weekend, so I didn't come to lecture Monday or Tuesday.
Of just last week or this one?
This recent week.
Oh, okay,
Yesterday
okay.
and the day before.
Okay, yes.
So I didn't pick up how to what's it called? Take roll.
Oh, how to take
Yeah,
attendance.
yeah. So when you did that,
Oh,
I was
yes.
looking, I was like, oh,